In this video, we're going to look at an experimental question where terminal voltage is measured across current and we relate it to the equation y equals mx plus c. So just to quickly remind you guys, the EMF is the total voltage that's provided by a cell or battery. It's being split up into two different types of voltages. There's the terminal voltage and what we call lost volts. There's lost volts because current has to flow through the internal resistance in order to reach the rest of the circuit. And then the terminal voltage is the voltage that flows through all the components except the internal resistance. So if there were multiple components in the whole circuit, it'd be the total voltage that flows through pretty much everything here. Here it's just the voltage across the variable resistor because that's the only component. Now that we've got that cleared up, from this experiment we can see that as current increases, terminal voltage decreases. And it's asking us to explain why this is the case. So looking at this equation, we know that EMF provided by a cell is constant. It doesn't change at all. But what happens when current increases? Well, actually, the lost volts, which is current multiplied by internal resistance, because internal resistance is constant, current increasing causes the number of lost volts to increase. If the number of lost volts is increasing, but EMF is still a constant number, then the terminal voltage has to decrease in order for them to still add up to that same EMF. For example, if you have 3 volts of terminal voltage and 3 volts of lost volts initially, that will lead to an EMF of 6 volts. But if the current increases so that the lost volts increases to 4, then the amount of terminal voltage would have to decrease to 2 in order for them to still add up to that same constant EMF of 6. So hopefully that helps explain it. So EMF is constant would get you 1 mark. And the second mark would be for mentioning that, an increase in current increases the number of lost volts, which then decreases the terminal voltage in order for the EMF to be constant. Hopefully that makes sense to you guys. You guys can rewind if you're not really too sure what I'm talking about. It says use the graph to find the EMF. So what we can realize is that this is a straight line graph, meaning it's in the form y equals mx plus c, where the y-axis, is replaced with terminal voltage and the x-axis is replaced with current. So let's make this in the form y equals mx plus c. Subtracting IR from both sides, we get that the terminal voltage is minus IR plus EMF. Putting this in the form y equals mx plus c, we can say that the y-axis is related to the terminal voltage, the x-axis is related to the current, in which case, comparing all the other like terms, I'm just going to get the highlighter tool out, we can say that the gradient is gives us minus the internal resistance, and the y-intercept gives us the EMF. So the y-intercept of this curve, which is roughly 1.52, sorry if you guys can't see that, is the EMF of this circuit. So let's fill that in, 1.52 volts. And then it also asks for the internal resistance. So we mentioned the gradient gives us minus the internal resistance. So what we need to do, using the fact that gradient is minus the internal resistance, we find the gradient and we multiply by minus 1 to get the internal resistance. To find the gradient, let's pick out 2 coordinates. Let's pick out this one, and this one looks pretty easy to use. Now the difference in current between them, 0 and 2.5 is 2.5. The difference in terminal voltage between 1.52 and 0.4 is, well, let's write it out. 1.52 take away 0.4, that's equal to 1.12. So minus the gradient, which is minus 1.12. Sorry about that, my handwriting's awful today. All divided by the change in current, which is 2.5, gives us the internal resistance. I'm just going to quickly do that on my calculator. So that's 1.12 divided by 2.5. That's equal to 0.448. Perfect. So that's the internal resistance of the cell. Moving on, it asks us to draw a line on the graph to show a cell with the same EMF but double the internal resistance. So the same EMF means that it crosses the y-axis at the same point, but double the internal resistance. Well, we know the gradient essentially gives us the internal resistance. So doubling the internal resistance means doubling the gradient. So it'll just be a line that's twice as sharp. So instead of crossing 0.4 volts at 2.5, it'll cross at 1.25. If that helps you draw that one. Something like that. It then asks us to draw the same EMF but no internal resistance. So if it's the gradient that determines the internal resistance. If there's no internal resistance, that means there's no gradient, or the gradient is 0. A line with gradient of 0 is just a horizontal line. and then it has the same EMF. So we just start it where it starts off, 1.52 volts, and then just draw a horizontal line to show no gradient and no internal resistance. Great. Let's now move on to this next part of the question. It tells you in this circuit, as shown here, the variable resistor is set to a value such that the current through the cell is 0.89 amps. So the current flowing through the cell and the circuit as a whole is 0.89 amps. By the way, that's the same as the current flowing through this variable resistor. The current would flow this way, and it's the same current because this resistor is in series with the whole circuit, so it takes that same amount of current in because current is the same in series. It then asks you to calculate the charge flowing through the cell every 15 seconds. So charge is equal to current multiplied by time. Because we know the current flowing through the cell, we can just multiply that by the time for which the current flows, and that will give you the value of charge. On top of that, you also have to remember the unit. So just putting that value to calculate, I got 13.4 to 3 significant figures, and then the unit would be coulombs, or you can write capital C. In case you're wondering how to spell coulombs, I'll just quickly spell it here. That's COULOMBS. Let's now move on to finding the energy dissipated per second. So always try to sort of think about what energy per second or energy per time actually means. It actually means power. So if we can use an alternative equation to find power, that's the same as finding the energy per second. Let's focus on finding the power through the internal resistance. What do we know about the internal resistance? We know the current flowing through it is 0.89 amps. And I think before we calculate the internal resistance, right? Yeah, we know the actual resistance of it. How can we use current and resistance to find power? Well, there's a specific equation, which is that it's equal to I squared R. This is on your equation sheet, by the way. So you take the current of 0.89, you square it, and you multiply by the internal resistance that we previously calculated for the cell, 0.448. And multiplying all those together will give you the power, which essentially is the energy per second. You might also notice that the unit is given as watts here, but that's another indication that you're actually just calculating the power. So I'm just going to quickly put that on my calculator, and you get a value of 0.355. That's your final answer for this question. Hopefully that all made sense to you guys. If you guys do have any questions, please let me know in the comments. Otherwise, be sure to like the video if it helped and subscribe. I'd appreciate it a lot. Thanks for watching.